This section is called Monte Carlo simulation. To explain Monte Carlo simulation and its benefits, we will first talk about other forecasting approaches that people could try. And then we will talk about Monte Carlo simulation directly, the concepts that it's based on. We'll give a detailed example and we'll show some sample outputs. And then we'll talk about sensitivity analysis, which comes out of Monte Carlo simulation directly. And then we'll wrap up with some other applications it could be used in and some of its benefits. So let's say somebody wanted to create a forecast. There are a number of different approaches that they could use. So if we see here, one of the first approaches they could use would be the point estimate forecast. And then going down this list, we see there's an increased level of risk adjustment to the forecast. So a point estimate forecast has essentially no risk adjustment. The following three have some. So that would be the point estimate forecast with the range, scenarios, and Monte Carlo simulation. Here is an example of a point estimate forecast. So we start out with the number of patients, here 2 million, market share 30%, and price per patient per year at $1,400. If we multiply all the numbers in this column, we end up with the forecast of $840 million. Now, if we use a definition of a blockbuster as a product that hits $1 billion or more in annual revenues, we can see that this product will not be a blockbuster. So this is a very typical example of a point estimate forecast. Let's critique this forecast. It is very unlikely that there will be exactly 2 million patients, and it's very unlikely that there will be exactly 30% market share, and that the price per patient will be on average $1,400 per year. The only thing we know for sure, however, is that this forecast will be wrong. Further, there's not even a chance that this product would be a blockbuster. And also, if research budgets are limited, which they always are, and we wanted to improve this forecast, which variable or variables should we focus in on? We can't tell from this analysis. So armed with the knowledge that there's always some range around a forecast, we go back to our original forecast of $840 million, and we put a plus or minus 20% range around it, or plus or minus $168 million. Based on this, we now can say that this product may be a blockbuster. Let's critique this forecast next. Is that all we can say, that the product may be a blockbuster? That doesn't add much information. It doesn't add much more than we already knew. And further, where did the plus or minus 20% come from? And why isn't it plus or minus 10% or 30% or 50%? We don't know, because there's no source for that plus or minus 20%. It just seemed reasonable. So now we try our third approach, which is forecast scenarios. So we reason that there's a downside case, most likely, and an upside case. And so for each one of these cases, we put in a different number for each variable. So for example, with patients, we put in 1.8 million for the downside case, 2 million for the most likely case, and 2.1 million for the upside case. And we do the same with market share and price per patient per year. And then what we do is we multiply down each column. And so for the downside case, we get a forecast of 432 million. For the most likely, again, we get 840 million. And for the upside case, we get 1.5 billion. And so from this, we can see that the product could be a blockbuster, but it probably won't be. Now, let's think about this a little bit more clearly. For each one of these variables, there's a probability of it being high or low, or in other words, ending up in the downside or the upside case. So let's just say it's 10% for number of patients being downside, 10% upside, 80% most likely. If we multiply down each column, the downside case has a 0.1% chance of happening. And the same with the upside case, 0.1%. And that's with 3 variables. If we put in 20 variables, The upside and downside case would have a 1 in 100 million trillion chance of occurring. So while looking at scenarios is a very good step, do we really want to waste management's time by looking at scenarios that have a 1 in 100 million trillion chance of occurring? And also notice how wide the range is for the final revenues, from $400 million to $1.5 billion. Does that really help with planning much to have such a wide range? Now let us introduce Monte Carlo simulation. And so here's a slide showing Monte Carlo simulation inputs and outputs. And what you'll notice is the inputs at the top are exactly like they were under the scenario case, with the downside, upside, and most likely. But here we're calling them low, most likely, and high. And but we don't now multiply down the columns like before. What we do is we treat each variable as an independent variable. And we're going to be sampling it between the low and the high. And what we end up with is the outputs at the bottom of the slide here. So we can say that the low case is $686 million. The most likely case is $865 million. And the high case is $1.05 billion. And we can say precisely that this product has an 18% chance of being a blockbuster. So here we're using exactly the same inputs as with the scenario case. However, we can say precisely that this product has an 18% chance of becoming a blockbuster. Further, the range of output revenues is much more reasonable, from 700 million to 1.0 billion, which is much better for planning purposes. Let's describe Monte Carlo in more detail. So, as is pretty obvious, it's named after a gambling resort in Monaco in southeastern France, and it's a technique to quantify risk to aid decision making. So to make decisions, we need to predict the future in some way, but the future is uncertain. And so what we need is a technique to help us quantify that risk. And what we do is we assign a probability distribution for each relevant input variable. And then we run a Monte Carlo simulation, and our output variables are also then expressed as probability distributions. So here you can see there's a distribution for sales and one for expenses, and the difference between these is the cash flow. So what types of variables can we use in a Monte Carlo simulation? The first is discrete variables. So discrete variables are on or off, yes or no. So for example, does an event happen? Does a product launch? What's the probability? The summation of the probabilities for all the branches must equal 100%. So if the product has a 70% chance of launching, there must be a 30% chance that it doesn't launch. Next, we have uniform distribution variables. And what that means is that within a range from X to Y, the variable is equally likely to fall anywhere within that range. And then next we have triangular distributions. So they have a peak in the middle, the most likely. So this variable is most likely to occur within the middle of the distribution, but there's a slight chance it would be on the high end and a slight chance it would be on the low end. The triangle need not be symmetrical. It could be skewed either direction. And one way that we typically set these variables is by using the surprise factor. So if you ask somebody, for example, what the temperature is outside, the temperature that they answered would be the most likely. But then you could ask them what would surprise them if it was actually, warmer than X. And that would be the high value. And then you'd ask them what would surprise them if it were lower than Y. And that would be the low value. Next, we have normal distributions, also called bell curves. And they're represented by probability density functions. And so these are typically defined by a mean and a standard deviation. Now, probability density functions, or PDFs, are actually equivalent to what's called a cumulative distribution function, or a CDF. So the distribution on the left and the right are identical. They're just presented in a different way, and they each have advantages. So we use them where we can take advantage of their particular features. So let's go through a very basic example here. So here we have three inputs for a forecast model. We have the population size, the market share, and the compliance rate. And you can see that each one of those is a distribution. The two bottom ones are skewed triangular distributions. The top one is a bell curve, a normal distribution. And what we do with the Monte Carlo simulation is we sample each distribution once. So for example, population, we sample it and we get 120,543. Then then market share, we sample it and we get 25%. And compliance, we sample it and get 63%. And then we multiply those out, and our final number of compliant patients is 18,986. And then we record that. And then we do that again. So we sample population, get 119,457. We sample market share, get 28%, compliance 68%. We end up with the answer of 22,744, and we save that. Then we do it again. We get the answer of 18,796. We do it again and again and again. We do it maybe 1,000 times. And our last case, we get the answer of 20,732. Now we have a distribution or a population of outcomes starting at the 18,000 at the top and ending at the 20,000 at the bottom. And what we do is we sort them and organize them and create a PDF or CDF of the output results. So let's talk about what the outputs can look like in a Monte Carlo simulation. So we have different distributions that we can get. And we can have, what we do have for each distribution, the mean, which is the average of the outputs, the median, which is the 50 percentile result, meaning half of the observations are higher and half are lower, and then the mode, the most frequent result, and then the standard deviation, which is a measure of the average distance of the observations from the mean. And so here are a few graphs showing some samples. Now, if we look at, say, the total prescription forecast, we can represent it both as a PDF and a CDF. So what's on the left and the right are identical data sets. They're just represented differently. Another output we could have would be X factory units, and that's represented both as a PDF and a CDF. Now, we've talked about PDFs and some of their advantages. Why do we even worry about cumulative distribution functions? And that's because they are very easy to use for looking at thresholds. So for example, for this particular result for this particular product, the result for this particular product shows that there's an 80% chance that prescriptions in 2018 for this product will equal 900,000 or less. And there's a 50% chance that prescriptions would equal 780,000 or less. And there's a 30% chance that prescriptions would equal 700,000 or less. And we get that by either starting at the horizontal axis or starting at the vertical axis and just drawing a line over to the curve. So for example, the very top result we have, we just start at the 80% probability, draw a line over, and see that it's at about 900,000. So there's an 80% chance that prescriptions will be 900,000 or less, which is the way these graphs are shown. On the next page, we have changed those mathematical representations into corporate functions. And you can see that you might want to set a target or a value based on the audience and its objectives. So for example, with manufacturing, we don't want to have stockouts. So we would say, okay, for manufacturing, we want to be 80% sure that we make enough product. For corporate financial planning, we want to be pretty much right in the middle and have our best estimate, which is at the 50% value. For Salesforce incentive compensation targets, maybe we want to make sure that the Salesforce reaches their targets most of the time. So we would set the Salesforce target lower so that there's only a 30% chance that we would be below that value. All the results we've been looking at so far have been results within one particular year. So if there's a range of results that go with each particular year, if we look out over time across years, we'll see that there's a range over time. And that can be well represented by deciles. So on this graph, we can see on the horizontal axis are different years, and on the vertical axis are gross revenues in millions. And what we see is that there is a line for each of the deciles we're interested in. So the bottom one is 10%, the next one up is 30%, 50%, 70%, 90%. And what these mean, so for example, the 10% decile number means that there's a 10% chance we'd be below that line and a 90% chance we'd be above it. The 30% line means there's a 30% chance we'd be below it, and a 70% chance we'd be above it. The 90% decile means that there's a 10% chance we'd be above it, 90% chance we'd be below it. Also on this graph, we can see there's a mean value and a point forecast. So the point forecast is just what comes out of the forecast model as the midpoints of all the distributions, the point forecast. The mean is actually calculated in the Monte Carlo simulation, and typically it's pretty close to the 50 percentile case as it is in this example. On the next graph, we have the same type of result for cash flow. You can see that it goes negative before this product launches because money is being spent before it comes back in. And then on the next graph, we can see unit forecasts, a unit forecast in terms of deciles. And so this is something that the manufacturing capacity could be built off of. And then finally, we have a table showing a lot of what we've just been talking about, but in terms of tabular results. So for example, with the NPV, we've got different percentiles that go with that, peak revenues, the cash flow nadir, the cash flow valley, the internal rate of return, and the year that the cash flows turn positive. So in addition to the percentiles, for each distribution, we can have a minimum, maximum, mean, median, standard deviation, and count. Now let's talk about sensitivity analysis. Sensitivity analysis is an important part of building and running forecast models, partly because it can answer the question of which variable or variables is driving the final answer and by how much. And this is important if you want to improve the model by getting better estimates of each of the inputs that are driving the answer. There are two types of sensitivity that we like to run in a forecast model. One is where every variable is changing at the same time, and then the other one is where each variable just changes from its high value to its low value one at a time. And you could do this manually, so you could take the first variable, put it at its low value, record the answer, put it at its high value, record the answer. And you could repeat this for all the variables, but it would take a long time. Within a Monte Carlo simulation, this happens as just part of the process as the model is run. So here we see an example of a graph created from that type of sensitivity analysis where we look at the high and low range for each of the variables, and then we order them so that the most important variable is at the top of this list. So for example, you can see it's diagnosed and treated cardiac survival time, and the The blue bar is if that value is at its low end, and the red bar is if it's at its high end. There's another type of sensitivity analysis where all the variables change at once, and then what we do is we look at which one is most closely correlated with the final answer here, NPV. So our top variable in this case is price per vial at launch, and it has a score of 15.1%. And again, we've ordered the variables so that the most important ones are at the top. So Monte Carlo simulation has a wide range of applicability. There's some listed on this slide here, such as sales forecasting, business development, R&D investment decisions, portfolio analysis, promotional levels and programs, product pricing, decisions whether to expand or contract the business, and other scenarios and examples. In summary, Monte Carlo simulation is a way to generate high-quality results and the decisions that those results can drive. And instead of letting the user worry about the probabilities, such as through scenarios, we just give Monte Carlo simulation the inputs it needs, let it run, and then it will give us the results. And the results it provides are probability-adjusted ranges for those results. Monte Carlo simulation helps us understand and measure uncertainty and risk. It tells us the probability of reaching certain thresholds, and it gives us sensitivity analysis to understand which variables are driving the answers. Furthermore, it creates more realistic best and worst cases than if we just look at scenarios directly. And it has the ability to run what-if analyses, and it's much faster turnaround time than if we did everything manually. And that's it for this tutorial. Thank you.